Now, this leads us to something that is very useful, and it's called the common ion effect. So the common ion effect is the shift in an ionic equilibrium caused by the addition of a solute that provides an ion that's common. So let's put that in more interesting words. All right, so if we have, this is acetic acid, and it's in equilibrium with the acetate ion. So that's our equilibrium, our acetic acid equilibrium. Well, what if we took and we added some acetate, but we didn't add it as acetic acid, but instead we added sodium acetate or potassium acetate? One of those where, you know, oops, not negative, the positive ion is ignoring, but we're adding the common ion from another source that's not the acid. Well, just think in terms of equilibrium, what's going to happen if you add some of the common ion, it's going to shift equilibrium to the left. So what's going to happen to the concentration of H3O plus? It's going to go down, meaning the acid will dissociate less, which means the pH will be higher. It'll be less acidic. So if you add a common ion, the equilibrium shifts, and in this case, because it's an acid, it will become less acidic. So that's the common ion effect. It's a shift in the equilibrium, shift to the left because of adding a common ion, a salt that has the common ion. So I said that the amount of H3O plus will decrease because the equilibrium is shifting to the left. Because the H3O plus goes down, the pH is going to go up. It's going to be less acidic. And so another way of saying that is the degree of ionization will decrease. Less of it will dissolve because of the common ion effect. So let's figure out what the pH of a solution will be of formic acid that also has the formate ion from a common ion, the sodium formate. What is the pH of this solution? And they're telling us the Ka for formic acid is 1.7 times 10 to the minus 4th. Again, just ignore the sodium because it comes from one of those strong bases, so we don't need to even consider it. It's just hanging around being a spectator. So we're basically adding the acid and the common ion. And they've given us the concentrations of the acid and then the concentration of the common ion. So here's our equilibrium. We don't have to set up two. We still have the same equilibrium. We have the acid, the formic acid, and then we have the formate ion. So when we set up our ice chart, we know that we don't start the formate with 0. We have some that we've added. So if we set up our ice chart, we have 0.025 formate or formic acid, and we have 0.018 formate. So instead of this being a 0, there's a number in there. But the rest of the equilibrium expression is the same, minus x plus x plus x. So 0.025 minus x, 0.018 plus x. We can set it up the same because we know the Ka expression and the Ka value. So we can plug that in. If we plug that in, we get this. That can be really complicated, but hopefully we're going to assume that x is very small. Because it's already, if you want to, you can do Ca over Ka, which is, take the bigger one, 0.025 divided by 0.0017. It's greater than 100, so you can ignore the minus x, and if you can ignore the minus x, you can also ignore the plus x because they're both going to be negligible. So we're assuming x is very small, and then we're going to keep those numbers. It's a very easy problem to solve, and x is equal to 2.4 times 10 to the minus 4th. So yes, indeed, it's much smaller than either of those two numbers. So our assumption was valid. And since x is equal to H3O plus, we can find the pH, 3.63. Just as a comparison, and you can do this problem for yourself, if you started out with 0.025 molar formic acid and you didn't have any of the sodium formate in the solution, then, and if you could solve that equation very easily, so that would have been 1.7 times 10 to the minus 4 equals x squared over 0.025 minus x. So we could have solved that one. So multiply both sides by 0.025, take the square root, you would find that the pH is 2.69. So in fact, we did see that equilibrium shifted to the left and our pH has gone up because of the common ion. And so this brings us to the idea of a buffer. And a buffer is just a solution that you may have heard of them before. It's a solution that is able to resist changes in pH when limited amounts of acids or bases are added to it. So what makes a buffer? A buffer has to contain either a weak acid with some of its conjugate base as a common ion, or a weak base with some of its conjugate acid as a common ion. And so it has both the acid and the conjugate base in equilibrium with each other. So if we consider a buffer that has the weak acid HA, then it also has to have some A minus around from another source, not from the acid itself, like from NaA. So what happens, so here's our buffer. So we have HA and we have A minus, both in equilibrium. So if you add a little bit of just strong acid, it will react with some of the A negative to form more HA. But if you add some strong base, then HA will form A minus. So what's happening, instead of having OH negative hanging around or H plus hanging around, what you're doing is you're shifting the ratio of HA to A minus. And because those are just shifting a little bit, your pH is really going to stay very consistent. It might change slightly, but not very much. So this is just another example. So let's say you have acetic acid and the acetate ion. So if you have both present in a buffer they might be equal. If you add a little bit of a strong acid, what's going to happen is the acid will take some of the acetate and convert it to acetic acid, so the ratio will just change a little bit. If you add a little bit of base, again, the ratio will just change a little bit, but the idea is you don't have any of this hanging around anymore because it's just converted this ratio, and you don't have any of this hanging around, it's just converted the ratio. And as long as the ratios are fairly consistent, the pH will only change. And you'll see when we do the next equation that it's really this ratio that matters. So here's just another example. On the left, solution on the left is not buffered, and the solution on the right is buffered. They're both pH 7 right now because they both have universal indicator added. So that's why that yellow color means pH 7. But one side is buffered and one side is not buffered. So what I'm going to do, just a few drops, 1 or 2 drops of sodium hydroxide has been added to both solutions. And notice that just 2 drops will change the pH from 7 down up to maybe 10. I mean, I don't know off the top of my head what it is, but that pH can change drastically, and it's just shown by the indicator color. But the buffered solution, even with the same number of drops of sodium hydroxide, has stayed basically the same pH 7. If you go back to the original solutions and add a few drops of hydrochloric acid, again, the unbuffered solution will turn very, very acidic. The pH might drop from 7 down to 3 or 4 very quickly, just with a few drops. But the buffered solution stays very close to 7 in this case. So buffer solutions are really, really important. Your body is made up of lots of different buffers to keep things pH balanced. So it is the ability to resist changes in pH when limited amounts of acid or base are added to it. So there's two important characteristics. One is buffer capacity and one is pH. Buffer capacity will just be how much acid or base is present. So in other words, how much of a buffer does it have? Can I add a few drops and it'll wreck the buffer? Or, now obviously if I added a whole lot of acid or a whole lot of base, eventually it would wreck the buffer. But it's sort of like how much of the acid or base can it absorb? That's its buffer capacity. And that will have to do with the concentrations of the two ions in the solution. So at some point the buffer is going to be wrecked. How much the buffer capacity will be defined by how much pH how much it can keep the pH, how much you can add of strong acid or strong base before the pH is wrecked. And then pH is the other thing, and the example I showed you on the last slide, they started out at pH 7, but you can have buffers that are any different pH. That you can, if you want a buffer that's pH 2, it's obviously very acidic, but again, the idea is that you can add more acid or base and not change the pH very much. So you can have buffers of any pH, and so it will just depend on the pair that you're choosing. It'll depend roughly on the Ka. So we can actually take our Ka expression and rewrite it. So how can you prepare a buffer of a given pH? Like I said, the buffer is where you pick a conjugate acid-base pair where the Ka is sort of approximately close to the pH that you want, or the H plus concentration. So there's actually something called a pKa, but you want the exponent of the Ka to be close to the pH that you want. So here's our generic acid with a conjugate base over here. And we can write our Ka expression. So this is nothing new, H plus times A minus over HA. What we can do is rearrange this equation, and it's not super important if you're not following, but what I did is you can see here that we multiplied, I multiplied both sides by HA. So that canceled, and then divide by A minus. And so what we have is H3O equals Ka times HA over A minus. Now, if you take the negative log of everything, the negative log of H plus we know is pH. The negative log of Ka is something called the pKa. And then here we have the negative log of HA over A minus. But if you make this positive and you invert that, we get our final equation, which is this one. And this one's called the Henderson-Hasselbalch equation. pH equals pKa plus log of the ratio of A minus to HA. So the main thing is you want a pH that's close to the pKa. And like I said, like acetic acid is 1.7 times 10 to the minus fifth. And so that's going to give a pKa somewhere around 5, maybe a little bit less than 5. So that if we wanted a pH of a buffer with a pH of 4, this would be a good acid. If we want this closer to 7, we're going to need to pick something that's got a Ka something around 10 to the minus 7. Okay, so let's look. So more generally, you can write this. So the conjugate base over the acid. And so it will have to do with, again, with this ratio. So what if this ratio, if the amount of base and the amount of acid were equal to each other? This ratio would be 1. If you take the log of 1, you get 0. And so at that point, pH equals pKa. So if you want the pH to equal pKa, then you just make these concentrations equal, and they will be. But if you want the pH to be slightly different than whatever the pKa is, you can adjust the ratio of these two a little bit to get the ratio that you need. So for example, let's say we want a pH of 4.90. So we need a conjugate acid-base pair, like I said, with a pKa close to that. And acetic acid, like I said, the Ka for acetic acid is 1.7 times 10 to the minus 5th. If you take the negative log of that, you get 4.77. So that's pretty close to 4.9. So like I said, what we're going to have to do is tweak the ratios of the conjugate acid to base to get it to be exactly 4.77. So if you look at that, so we have pH, that's what we want the buffer to be. We have pKa. So if we subtract that, what do we get? 0.13. 0.13 equals log of the acetate ion to the acetic acid ion. If you take the inverse log of both sides, we get 10 raised to the 0.13 is 1.35. So basically you would need your concentration of acetate to be 1.35 times that of the acetic acid. So if you made that 1 molar, you would make that 1.35 molar or whatever ratio you wanted to, but it should be 1.35 times as big as that. We're not going to do a whole lot of calculations with this, but I just wanted you to kind of keep that in mind, and it'll be important when we do the next when we talk about titrations. All right, so if we wanted to, we could go back and use this to solve our previous common ion problem. So an aqueous solution, remember this was it, an aqueous solution that was 0.025 molar in formic acid and 0.018 molar in sodium formate. What is the pH of this solution? And the Ka is 1.7 times 10 to the minus 4th. Now, we are able to do it just fine. So there's nothing wrong with using that equation. Probably using this equation would be a little quicker, but really they're both the same equation. This is just a rearrangement of the other. So you don't have to do this, but I was just showing you. So what is the pH? Well, we can find the pKa. pKa is just negative log of the Ka. And then we have the base, 0.018, divided by the acid, 0.025. So the negative log of 1.7 times 10 to the minus 4th is 3.77. And then this ratio is 0.72. So if we take the log of 0.72, we get negative 0.14. Do be careful with the signs. So 3.77 minus 0.14 gives us a pH of 3.63. And that's what we got when we did the problem the other way.